Hello and welcome to another lecture on human-like artificial agents. Today we will focus on navigation and steering behaviors specifically. We will begin with the motivation, which shows that navigation of groups is quite a challenge. Following video will show various games with problematic navigation cases. I will leave you to absorb it and then we will break those cases one by one. So the first example is from StarCraft 2, which actually has done the navigation of units quite well. However, even StarCraft is not considering alternative paths for unit groups, like those red lines. That's because pathfinding is quite costly, so you usually find a path for the whole group and then let all units to follow it. Notice that some units actually found an alternative path. That's because you usually create routines that detect stacks. And if that happens, one thing you can do is to replan, though you must be careful as the number of replanning per tick cannot be high. Next example is from Empire Total War. Here we have a cavalry moving forward. If you want the group navigation to look organic, you can have soldiers synchronizing on a leader. Thus, the leader finds a path and all other units will try to follow the leader. Unfortunately, soldiers are using local steering technique, which can get them stuck. If you fail to code your stuck detectors well, or the unit stuck again after replanning, you are doomed. So here the problem is the combination of local technique with problematic environment features. Another kind of problem happens when you want your units to have a collision radius, which you should, as non-overlapping movement looks definitely more intelligible. However, in such a case, a player can easily create a situation where one unit will block the movement of the others. Now, when you are path planning, you typically do not take dynamic objects such as units into account, because the player may reposition them anyway. Therefore, the pathfinding will return a path leading through such units. Or even worse, a player can send two groups along collision paths, something which is even harder to detect and overcome. Then the Company of Heroes case. This one is a bit unfair. The game is created as something that has rather open space. Therefore, it did not make sense to create some sophisticated code for navigation of units. Even more because you could not have that many of them often. But we can see what problems local steering techniques can create. Trying to move a lot of units through the small passage will result in units being unable to cross, and thus will start to seek other paths around the obstacle. Finally, one thing players like in strategic games are formations, though it is hard to make one. Therefore, some games like Rise of Nations are trying to maintain whatever formation you try to create. However, as a player may choose a location that does not have enough space for the formation, The question is, what to do in such a case? The most likely nothing is the best response. Stop movement of your units and let the player to solve the situation. To summarize, a group navigation is a task that typically occurs in real-time strategic games, when a player issues a move command towards some location X to n units at once. The n can be sometimes quite high, like 100, and the problem is how to reach that location with those units in an intelligible way. The intelligible can be characterized as starting the movement fast in a few frames at maximum, maintain coherence of the group along the way, do not overlap units while moving, and do not get trapped by dynamic obstacles or placed buildings. And actually that's an open problem, as it always faces the real-time requirement. You have to do it fast, even n-log n may be a problem. Finally, let's pronounce why those requirements are hard to meet. First, starting the movement in a few frames is hard if you have 100 units, large map, with many narrow passages and only a few frames to decide which way to start moving. Then, coherence of the group goes against avoiding local obstacles on the path, or taking local detours. Many use cases are associated with that, and players typically have different opinions on what is right. Third, units with collision radius are a source of potential blocks. They can have different dimensions, which makes the pathfinding and group coherence even harder. Finally, as the games are dynamic and you have a player changing mind, navigating through maps where paths are changing, buildings are created and destroyed, makes one wonder whether there is something like the best path. And so, when creating RTS games, if possible, one tries to relax this problem. Let's continue with the video where we will see various ways how to tackle the problem. Again, I will not be commenting on that. Now, let's break down those cases again. First, Knights and Merchants, fully grid-based world, which each cell can have one unit at maximum. No units are bigger than one cell. In such a scenario, it is easy to define edge cases for dynamic situations, like having two groups walking against each other. Even though the solution is complete, it is slow, looks quite unnatural, and making the combat in this game a bit chess-like. Anyone recognizes this game? I haven't played this one, but lining emergent behavior can be seen in many real-time strategic games around 2000. For instance, in StarCraft 1, Zerglings are doing the same. This happens when you assign the same path to every unit, and you do not use local steering techniques for the group movement. But maybe it's not a bad idea. If you actually use those steering techniques and you parameterize them wrong, it can backfire. Units might start getting astray from the original path if you are not careful enough, and if you decide to stop them if they deviate too far, you might get into a situation like where units fail to reach their destination, like in the Rise of Nations. The same game and units of asymmetric sizes and different speeds. Here the game uses the relaxation of collision radius. If it finds the situation not to be easily solvable, it just lets units to pass through. Finally, dawn of war. Here units have very small collision radius and probably simple steering rule that reacts to collision. If you bump something, generate a force that leads out of the collision. It produces funny turnings of units from time to time. So, we have seen that the navigation is actually a result of three things. The first is pathfinding, that usually finds the shortest path and is assigned to all units in the group. Then, the solution deviates in the second step, and that is a path following that is trying to locally resolve or avoid collisions. Finally, the third component are stuck detectors. When you detect that local technique is not working, you stop the unit and typically replan, which is unfortunately costly and may not even help you, as pathfinding is not taking dynamic obstacles into account. We will talk about this more during the lecture on pathfinding. As the result, all those stages are intertwined. Their implementations affect each other in the end. Today, we will have a closer look on the second part, the local navigation techniques known in games as steering behaviors. Looking at our architecture, we are discussing the locomotion layer of IVA Mind. And here is a simple diagram how respective layers connect on each other. Action selection are setting us with goals and locations to reach. The path planning is providing us with a list of path points. And path following is trying to compute next location to reach in a few frames. This is then picked by animation controller, which are trying to match correct animations with the context of environment and the movement speed. You might ask, why should we care about steering behaviors? Well, in the nature, simple local techniques can lead to fascinating emergent behaviors, like flocking of birds. Or fish schools that seems to react to predators in a very coordinated and intelligent way. But they are not, they are small, they just execute a few steering rules in high distributed numbers. And we can replicate that actually. In the following video, voids, the little dots, are not path planning, they just steer. I will let you watch the video again without comments. Try to match following artificial cases with what you have seen so far. Again, let's break down those cases and comment on strengths and weaknesses of local steering techniques. So, here you could have seen we can replicate the flocking. Of course, birds were changing directions, but that can be simulated with addition of wandering behavior. What is great about steering behaviors is that they can be easily combined. Here we combine flocking, one set of rules, with obstacle avoidance, another set of rules, which just blends together. Here we are even adding attraction. If you watch the video again, you will notice blue rectangles, which acts as attractors for buoys. However, it's easy to replicate the problems we have seen in games. As steering is a local technique, it can easily lead into splitting the group in two. Also, steering rules are hard to parameterize. What worked once might not work next time. As there are a lot of numbers crunched every frame, the system is quite chaotic and hard to debug. It's a lot about tweaking and testing. So, how can we define steering behaviors? We can say it's a framework for controlling low-level movement of autonomous agents, the means of locomotion. Steering behaviors are technically based on forces that are adjusted every frame. That's why they are so easy to combine, computationally cheap, and produce smooth paths. But that's also why they are hard to parameterize. Bear in mind its local technique. It never works with long look-aheads. It's just projecting the velocities of agents around, as that is the only thing it knows about them. However, you can have a path to be an input for steerings. As we will see later on, we can have a steering rule trying to stick to the path. Finally, even though steering behaviors works per agent, group of agents are exhibiting emergent group behaviors, which would be very hard to orchestrate otherwise. Originally, steering behaviors were invented by Craig Reynolds around 1983, but it got its spot in sunlight during GDC 1999, where a classic source on steering behaviors was presented. Reynolds created a set of Java applets exemplifying steering behaviors. They are quite outdated nowadays, but still runnable through Internet Explorer 11 that can still be found in Windows 10. Let's now talk about movement algorithm steerings are embedded in and assumes. They are based on a very simplified model of a car. First, we execute steering rules that are active and sum them up. This gives us the result force affecting the agent. The agent might have a mass, so we compute an acceleration out of that. Each agent should have the maximum acceleration set, otherwise we could get extreme values in extreme cases. Then we compute a new velocity given the previous one, the acceleration and the timestamp. Clamp it again not to get into extreme numbers, and so we can compute new position for the agent as well as obtaining the current speed and orientation. Now the last three steps might not be rewritten into the simulation or applied to the agent. As agents may have complex animation controllers, those values might become inputs for it. The position computed thus becomes next target to reach for the animation controller. And the controller may, for instance, switch between walking and running given the distance and desired speed, or different turning animation according to desired look direction. Now, a lot of steering behaviors, or steering rules if you wish, can take place in the first step of steering movement algorithm. Here is the list of original Reynolds behaviors. And we will go through the most of them. For the rest, I would like you to point you to the Reynolds page about steering behaviors. The first steering behavior is seek and flee. The seek behavior steers agent towards a static target, while flee away from a static target. Technically, it is easy. We just combine current velocity with a desired one that differs for seek and flee only in a minus sign. Here is what it looks like. Now, you may have noticed that seek behavior were overshooting the target, which is not always desirable. Therefore, you might want to introduce slowdowns. Technically, you need to define a slowing area that clip the maximum speed as you approach the target. And that's how it works. As seek and flee, except that was for static objects. For dynamic ones, we have pursue and evade. It actually is a seek behavior, or you just modify the location you want to arrive at, given the velocity of your target, and vice versa for the modification of flee. Here is the showcase. Another typical use case for games is wandering around the environment, though it cannot be widely applied everywhere. This steering is generating a wander force that it changes slightly every frame. You define one circle for generating the random offset and another big circle for constraining the result force. And the result is surprisingly good. This could have been paired with flocking, with what we have seen previously in order to replicate the flocking of birds more believably. And speaking of flocking, that behavior is actually the result of 3 steering rules: separation, alignment, and cohesion. Roughly speaking, you first find voids which are around you, which forms your local flock, and then you compute those 3 forces. First, the separation, which dictates you not to get too close to nearby flockmates. Second, the alignment, which steers voids to have the same velocity as the average of velocities of nearby flockmates. And third, the cohesion tries to make the void to be in the center of the local flock. You can see that separation and cohesion are fighting each other, so you need to take care to parameterize those rules correctly as they change the result behavior. And here is the result we have actually already seen. If you would like to experiment with that, you can download the following code that is runnable using Processing Framework. It allows you to play with the voids. Now let's move to other group of steering behaviors. The first is leader following. We have more or less seen in Empire Total War. This steering is composed of arrival and separation. You want to arrive to leader's position, but you also want not to bump to other agents. This is easily combined with formations. If you define a different relative positions to the leader for each unit, you will get quite nice formation movement result. Here is the example, but without formations, of course. Another highly useful steering behavior is a path following that works with a path as an input from the path following step. You define a corridor how far the agent can steer from the path, or you establish this corridor given the path surroundings in the environment. And then you project the agent location into a future to see if it is going to astray from the corridor or not. If it will get away from the corridor, you perform seek towards the point you project onto the path. And the result looks quite good. And you can combine it with separation to produce quite nice flow of agents along the path. The last example is unaligned collision avoidance that is used if you do not assume cooperation of other agents. First, you decide on dangerous areas which threatens to collide with your movement. Find the most threatening one, and given that, you generate avoidance force, possibly decelerating or accelerating, to resolve the collision with the most imminent threat. Here is the result. Now, that was Reynolds, but there is another area that needs to watch out for collisions with other agents and the environment, and that is robotics. Nowadays, robotics is another source of inspiration for solving the local path following step of navigation for agents. We will present two basic techniques for avoiding collisions with moving obstacles, and that is velocity obstacle and reciprocal velocity obstacle, which are now a classic, if a bit outdated approaches to the problem. So first, velocity obstacle. Velocity obstacle for agent A with respect to agent B are defined as all velocities of agent A that will result in collision with B, given the assumption B will not change its velocity. It has a nice vector definition that has a good geometry interpretation, so let's construct that step by step. First, we have two agents A and B with their collision radii. Agent A is aware of agent B. That is, it knows about B's position and velocity. Example situation is depicted here. Now we construct a circle around B in which a collision for A would occur. That is, we take radius of A and add it to B. The notation of -a here is a bit misleading. In the original source, it is treated as A that has been repivoted to the center of B, and then you perform the Minkowski sum. With respect to the future collision, it is not velocities that concerns us, but their composition. That is, the velocity with which agent A will be getting closer to B. Now we step back a bit and start considering all possible velocities A might have. So now VA is not the current velocity of A, but really any velocity. And we consider all rays with which we can be getting closer to or taking distance from B. And those rays that actually cross the dangerous boundary around B are forming the velocity obstacle. And if we translate this with current velocity of B, we get an area of speeds for A we want to avoid. In other words, if A wants to avoid collision with B, it better picks a speed outside of pictured velocity obstacle. That is, agent A will compute velocity obstacle for B every frame and chooses its speed outside of that velocity obstacle. All good. Unfortunately, velocity obstacles are often producing unwanted behaviors, like oscillation during resolution of conflicts. Consider two agents walking directly against each other. In the first step, they realize that they are both in collision. So they change their heading, resulting in a no collision next step. So agents try to restore their original heading, getting into the collision again, and so on and so on. And so their velocities will oscillate. That's where reciprocal velocity obstacle steps in and smooths this out. Now consider the year of the source, 2008. This was not available when majority of RTS games were being developed. But back to RVOs. The property of velocity obstacle is that they are symmetric. If agent A perceives the collision, so does agent B presumably. And if both agents changes the velocity the same way, it won't help them. So the idea of RVO is that agents should assume cooperation in resolution of this conflict, and each agent should perform half of the avoidance. Here is the formal definition. In a nutshell, RVO is VO that is translated by the average of A and B's speed. So each agent will perceive the velocity obstacle to be slightly off. And so if every agent will take the same measurement, that is, to navigate towards the tip of this triangle, then they will not get into collision. And it can be proved that if both agents commit to this strategy, the result will be collision-free, while also oscillation-free. This particular theorem states that when agent changes their velocities, the old velocity VA is within new RVO, and thus agent A will not return to that again, assuming both agents will do the same. However, RVOs are not without problems. Agents do not communicate, so if one of them is not able to resolve the collision RVO way, for instance because there is a wall next to it, then the collision is not avoided. Such a problem can be alleviated, for instance, by iterative computation of velocities for agents before you actually apply them. However, this approach is computationally intensive. So, that's it for today. Thanks for watching. Bye!